All right, 11.6 is segment relationships in circles. Find the lengths of segments formed by lines that intersect circles and use the lengths of segments in circles to solve problems. Those are your two objectives, so let's try and do that. So there's our awesome vocabulary. All right, so our chord product theorem basically tells us that when two chords cut each other in half, or not in half, sorry, when they cut into each other, this happens. So notice how AE equals EB, or AE times EB equals CE times ED. Notice the red, blue, green, purple. Now over here, notice what chords are getting cut in half. So on this side there was a blank, blank, equal sign, blank times blank. On this side over here, it was AE and EB. Now notice how that was the same, those are the same two lines from the same big line. You take the small line from each side and you multiply it to the small side of each of the other one. So this over here is CE times ED. So don't make sure you don't get these switched up. You have to pair up the AE with the EB. You have to pair up the CE and the ED. As far as what side you put them on, it does not matter because it's multiplication. It's going to be the same thing whether you flip it or not. But when you set up your multiplication, you have to do the same lines from each one. You can't do green times blue equals red times purple, or purple times blue equals green times red. You have to do the same lines equal the other same line. All right, so let's solve this problem. Find the value of x and the length of each chord. So first, let's find the value of x. I see that my two chords cross each other, so I know this chord breaks up into two pieces. Those two pieces multiplied by each other, GJ times G, or JH, is going to equal these two pieces multiplied by this piece and this piece. So I've got equals FJ times JE. All right, so I know GJ was 14. JH is X. FG is 7. JE is 10. So I have 14x equals 70. Divide by 14. I get x equals 5. All right, so notice what they're asking for. Find the value of x and the length of each chord. So I've done the first part. I found x. Now I just need to go in and say what the chords are. Well, what is a chord? A chord is a line that goes through the circle. So I need to find FE and GH. I don't just need to find all of these. I need to find the whole length. So 3 answers. X equals 5. I need to find out what GH is and what FE is. Well, GH, you just go from G, count all the way to J, you get 14, count 5 more, and you get 19. So GH is 19. Come over here to F. I need to count all the way to E. I go 7, I go 10 more, I get 17. So it's simple as that. All right, let's just do one more problem real quick just to make sure we know what we're doing. I'm going to go ahead and just breeze through it real quick. 8 times x equals 6 times 5. 8x equals 30. X equals 3.75. All right, the fact that that's 3.75 tells me AB is going to be 11. 6 and 5 make 11. CD is going to be 11.75. All right, so real quick explanation on this. I see that my two lines cut each other, so I take the small part of this one, multiply it to the small part of this one, set it equal to the small part of this one times the small part of this one. I got 8x equals 30, divide by 8, 3.75 was my x, and then I just plug it back into here to figure out what the lengths of my chords are. All right. A secant, I think one of these are a buzzword. Let's see, let's make secant segment. That'll be your buzzword, why not? Secant segment is a segment of a secant with at least one endpoint on the circle. So it's a segment because it doesn't continue. So notice how it's not a chord because it keeps going, but it's a secant segment because it stops. Secants normally just keep on going, but a secant segment stops on the circle. All right, so a secant segment is a segment of a secant with at least one endpoint on the circle. An external secant segment is a secant segment that lies in the exterior of the circle with one endpoint on the circle. So notice PM, NM, KM, and JM are all secant segments of the circle Q. NM and JM are external secants. So they're all secants in their own right, but these are specific because they're outside of it. These are external secants. All right, so we of course have this cool property that we can apply to them. So I've got AE is the whole length. I can take the entire secant segment, multiply it by the external secant segment, and set it equal to the other one times this external secant segment. And I only do that because they meet at the same point. So the theorem says, if two secants intersect in the exterior of a circle, then the product of the lengths of one secant segment and its external secant segment equals the product of the lengths of the other secant segment and its external segment. Basically, the whole times the outside equals the whole times the outside. I would write this down next to it. And write this diagram down. If you want to do red and blue, that's fine. Notice how you're doing red times red, blue times blue. If you want to even make this all 4 different colors, so it even helps you a little better. So let's say this BE is also green. And we'll make DE purple. If you want to. If you're good with everything else, then just leave it at that. So I'm taking red times green equals blue times purple. Right there. Make sure you're able to do this. Copy this down. Of course, we'll do an example real quick for you. But we do have to learn one more theorem. Or did we just learn that twice? Nope, we're good. All right, example. Find the value of x and the length of each secant segment. So what I need to do is figure out what property I'm going to use. I'm probably going to use the one I just learned. I am. So I need to figure out what the whole length is. I'm going to have whole times outside equals whole times outside. All right, let's do the GE. That's supposed to say outside. Just pretend it does. Here I got the outside. I know this is going to be 8. But what's the whole length? If I go X amount and 8 more, this X has to be a number. I don't know what it is. So think of a number line. If this is X and this is 2, how could I represent this entire number line? Well, I could just write X plus 2. So the whole segment is going to be X plus 2, or X plus 8. X plus 8. This goes away. This was just a quick example to explain why we're taking X plus 8 and not just X. Because again, we want the whole outside. We want the whole secant segment. The whole secant segment is X plus 8. The external secant segment is 8. Now you can go ahead and distribute that if you want, but I'm going to show you why you might want to just hold on to it right there and leave it there. Because I'm going to be taking equal to the whole segment. I go 9 and I go 7 more. I have 16. I'm going to multiply it by the external of 7. All right, I'm going to combine these. I get X plus 8. Again, leave the 8 on the outside. Don't distribute it yet. 1, 1, 2. Now, instead of distributing the 8 into here, let's go ahead and divide the 8 out and move it over here. So I'm going to divide this. Since it's on the outside of the parentheses, I'm multiplying it. So I divide it out. I get X plus 8 equals 14. So that was a lot easier instead of distributing and then subtracting and then dividing. So now I can just subtract the 8 over, sorry, this is supposed to be just 14. X plus 8 equals 14. Subtract the 6, or subtract the 8. I get X equals 6. All right, since X equals 6, I can now find the entire secant segment. Since DE, all the information is there, I've got DE equals 16. And since I now know that this is 6, I know that G all the way to E is 14. All right, a tangent segment. Again, we already know what the tangent line is. A tangent line is a line that keeps on going forever and ever and ever, like this. It stops only at one point, except mine never do. It goes all the way, it stops at one point, and gosh dang it, it keeps going all the way forever and ever. A tangent segment stops, and for this one, it stops at A. Okay, so a tangent segment is a segment of a tangent with one endpoint on the circle, and that's pretty much it. Tangent segment is your second buzzword. AB and AC are tangent segments because, again, they start on the outside, they go to the circle, they only touch at one point, and they stop. If it kept going, we would just call it a tangent. All right, so we got a secant tangent product property. Yes. So notice how I've got a tangent going on and a secant going on. Again, you're going to take the whole secant, multiply it by the external. And since I only have a tangent, I'm going to go ahead and square it, and that's what I'm going to set equal to. This is the one that I think we're going to be fine remembering the last one, but the secant tangent product theorem, this is the one that people are either going to forget to square this, or they're not going to multiply by the whole thing, they're just going to multiply by this and this. You need to multiply the whole thing times the outside, equal it to the other tangent squared, or the tangent squared. All right, so real quick example. Let's find the value of x. So I see that I have a secant and a tangent, so I'm going to use the secant tangent product theorem. I know that the entire length is 20. So LM, this is going to be the theorem I'm going to use too. LM is the secant. I'm going to multiply it by the external secant, and I've set it equal to the tangent, which is LK squared. So let's plug in everything I know. I know LM is 20. JL is 5, LK is X. I get 100 equals X squared, square root it all to get rid of it. I get X equals plus or minus 10. However, only one of these is the correct answer, and the answer is the positive one. We do not want negative 10 because our value is a length. We don't want a negative length. We can't have negative length. If I measure the distance of your desk or table, it's not going to be a negative number. Length and degrees are all going to be positive for geometry. So x equals just 10.